So good morning, everyone. My name is Ricard Montala. I'm a PhD student at the Polytechnical University of Catalonia. And today I'm going to talk about this project in which we combine active flow control with deep reinforcement learning. But first, a little bit of motivation and objectives. Here I'm showing you a plot which shows how the CO2 emissions of the aviation sector has changed over the last years, in which you can see this increase by the 30%. Of course, then we have this sudden decrease. This was the COVID-19 situation. But now we have recovered the normal levels of emissions, and indeed, this is still increasing. Also, if we look to this second plot, you will see that the aviation sector in Europe, compared to the other transport modes, represents the one with the higher increase in emissions. So this reflects at the end that we need to think about new ways of reducing these emissions. And one way of doing so could be, for example, reducing drag. Less drag means less fuel consumption and, of course, less emissions. And to tackle this problem, we can think about two traditional main approaches, passive flow control, in which we mainly modify the geometry of our body to achieve the desired effect of reducing drag, increase lift, or whatever we want. Or on the other hand, active flow control. In this approach, we use extra energy to create some kind of interaction with the flow. For instance, we could use jets, such as in this case, that was conducted by my colleagues, Yvette, Oriol, and Ricard, in which by using synthetic jets, as you can see in the image, on the leading edge of the wing, they achieved to reduce this massive separation on the wing and increase the lift by the 90% and reduce the drag by the 67%. So very promising results by active flow control, but we can see some drawbacks. First of all, we need to optimize several parameters, and this is not an easy task. It may require several iterations, and even this doesn't guarantee you that you succeed. And second of all, you are using a single frequency on the velocity of the jet. So you are like targeting only very specific coherent structures in the flow, which may mean that at the end you can achieve a given maximum amount of drag reduction. And that's why we want to use deep reinforcement learning to discover much more complex active flow control laws that allow us to push the limits of drag reduction in wings. So what is deep reinforcement learning? I will try to go fast here because we've already seen this morning in some talks. We have an environment, in our case, the CFD simulation, and an agent. In deep reinforcement learning, this is an artificial neuronal network. And the environment sends the state to the agent. This state could be, for instance, some sensors that are placed in the domain of the fluid. And we send as an input, for instance, the pressure of these sensors. Then the agent receives this state and gives back as an action that is applied to the environment again. For instance, this could be the velocity of the jets. But of course, at the beginning, since this neuronal network is not trained, it will give us some random actuations. So we need to adjust the weights and biases and train the agent. And to do so, the environment also sends the reward. This reward is the quantity that we aim to optimize. This could be, for instance, the drag coefficient, the lift coefficient, a combination of both, or other quantities that you can imagine. But then the agent, by engaging in a trial and error process, and by knowing how each action has produced a different reward, it will refine accordingly to optimize the reward. In our case, the environment is SOT2D. This is an in-house code developed at the Barcelona Supercomputing Center. It's a spectral element method code. It's GPU enabled. This is very important because at the end, one of the bottlenecks of this framework of deep reinforcement learning with fluid dynamics is the collection of experiences to train the model. Once you have these experiences to update the weight and biases of the neural network is quite fast because at the end, the neural network is quite small. So yeah, the most time-consuming part is the collection of experiences. So using a very fast solver that use GPU accelerators, it's a good thing in this for this framework. If you are more interested about this code, I invite you to go this afternoon to the talk by my colleague Jordi Muela, who will talk about the scalability and performance of such a deep. And on the other hand, for the agent, we are using a very well-known Python library that is called Diffie agents for deep reinforcement learning. And here we have a problem. On one side, we have a low-level programming language, and on the other side, a high-level programming language. So how do we couple them? In our case, we are using a Redis in-memory database managed by this library called SmartSim, which creates a an in-memory database so that both the Fortran instances and the Python instances can write and read from this database and then do this exchange of information. This framework was first implemented by my colleagues Bernat, Fran, Jan, Ricardo, and Oriol in this work in which they managed to reduce a separation bubble in a turbulent boundary layer. The whole framework that couples sought to deal with this Python library Diffie agent is called SmartSOT. It's open source, so you can go and check it. And now the idea is to try how this framework works for black bodies. That's why we use this case that was already trained in the literature. It's the flow past a cylinder at a Reynolds number 100, so it's laminar. And in this case, as I've told you before, the most time-consuming part is to collect experiences from the CFD environment. So to accelerate the training, we are using a DRL parallelization that was proposed in this work so as to collect experiences from several independent simulations simultaneously. So for instance, the cylinder domain along the invariant direction, we can divide it in several pseudo environments. And also we can consider, for instance, 4 CFD simulations in parallel, so that at the end we have 10 plus 10 plus 10 plus 10, 40 environments, all creating different experiences that are then sent to the same agent. And then, of course, this agent will give back the mass flow rate that is applied to each of these environments. In reality, this mass flow rate is used to compute this velocity profile that is the boundary conditions that we applied in the CFD simulations. For the state, we are using these sensors. Each environment has one slice of this, and the input of the agent has a total size of 255 sensors. Because we are not only using one slice, we're also using the 2 neighboring slices of the neighboring environments. For the reward, this is the expression that we are employing. It has a first part that accounts for drag reduction. It's the baseline drag minus the drag. And on the other hand, we have a second part that accounts for reducing the amplitude of the lift oscillations. So it's the absolute value of the lift coefficient. This reward is used to compute this second reward that is in reality the reward that we use to train the model. That it has a first part that is the local reward of each environment, plus a second part that is the mean reward of all the environments. Each term multiplied by a weighting factor beta to adjust the weight of each term. For the training is divided in episodes. Here we considered 50 episodes of a length of 36 time units. This is roughly 6 vortex shadings. And in each episode, we applied 120 actions, so that by the end of the episode, by collecting all these experiences produced by the different environments, we update and adjust the weights and biases of the neural network, the agent. And here I'm showing you how the mean reward evolves along the different episodes in the training. You see how in black, the total reward, in red, the drag contribution, and in blue, the lift contribution, according to the expression that I showed you in the previous slides. And you see how the agent successfully learns how to reduce drag and reduce also the oscillations of the lift coefficient. Just for you to know, this is the computational cost of this case. This was run at the Mare Nostrum 5 machine in the accelerated partition using one node, which contains 4 GPUs, and it took about 26 hours. So this leads to a total cost of 100 GPU hours, more or less. So once we train the model, these are the results using the learn policy. We start applying the DRL control at the time unit equal to 50. So you see, this is the action. You see how at the beginning we have a little transient and it converges to a periodic, nearly periodic control. And here I'm showing you the lift and drag coefficients. You see how after applying the DRL control, the lift coefficient, the amplitude reduces considerably. Indeed, we saw a reduction of the standard deviation of about 78%. And also you see that after activating the control, the drag reduced as well by the 9%. For the natural vortex shedding frequency of this cylinder was 0.70, and once we applied the DRL control, this frequency was delayed and reduced to 0.16. So yeah, the idea is that the DRL control learned to do somehow a kind of an opposite control in which it reduces the intensity of the vortex, the shear layers that are formed at the top and bottom parts of the cylinder, and by doing so, it reduces the vertical motion of the vortex shedding and hence enlarges the wake along the stringwise direction. So here I'm showing you the pressure coefficient so that you can see that this leads to a higher pressure at the rear part of the cylinder and hence reduces the drag, the total drag of this case. So once we have tried our framework for a relatively simple case, the idea is to move towards a more realistic industrial scenario, such as the flow past a wing at a Reynolds number 60,000 and an angle of attack of 14. As I showed you at the beginning of the presentation, this case at these conditions has a massive flow separation. So the idea is to control that separation and reduce it. Here we are performing LES simulations with a maze of 5 million grid points. This could seem a little bit coarse, but we are obtaining fairly good results compared to the literature for the baseline case, for the lift, drag coefficients, and also for the pressure distribution. And we also here tested a classical active flow control to see how it worked, and achieving a lift increase of 24% and a drag reduction of 52%. Here I'm comparing the results of the baseline versus this classical control, in which we apply synthetic jets on the leading edge of the wing. And the idea now is to try to see if we can go further using the DRL control. But this is still ongoing. We are still training the model. But just for you to know, we are running 20 CFD simulations in parallel, each one containing 2 pseudo environments. So we are collecting the information from 40 environments in parallel to train the agent. As stated, we are using these sensors. Each environment contains one of these slices of sensors. We mainly have located the sensors in the separation bubble and also some sensors in the shear layer on the leading edge, so that the agent somehow knows some about the physics that are going on here, since they play an important role then in the development of the real flow. For the action, we apply an action with the frequency of the action is 10 times faster than the frequency that we apply for the classical control. And the episode length is about 10 time units. This was selected accordingly to this. This is the lift and drag coefficients for the classical control. And you see that it takes roughly 10 time units to reach this statistically steady state. And that's why we selected this episode length. This is an estimation of the computational cost, assuming that we will require 50 episodes. Of course, we don't know this yet. But the machine is, again, Mare Nostrum 5. We are running this on 80 GPUs, and we expect it to take 14 days. So this is a total cost of around 25,000 GPU hours. For the moment, we have only 7 episodes. Each of these windows represents an episode. And here I'm plotting you the lift and drag coefficients. And the reward that we are using to train this is quite similar to the reward that we use for the cylinder, that has a first part that aims to reduce the drag and a second part that aims to increase the lift. As you can see, by the end of the episodes, for the moment, we are still obtaining the same drag and lift coefficients. So the reward for the moment is still a flat lane. So we are still doing this. We are training this now, and hopefully we will have some results early. So please stay tuned if you want to know more about this case. This is the end of my presentation. Thank you very much. And if you have any questions, I will be happy to answer.